So in chapter 14, we're going to talk about the next functional group, which are alcohols. And alcohol functional groups are ones where we have an OH group attached to a carbon. And as a functional group, this is called an alcohol. Sometimes we'll talk about the OH group being a hydroxyl group or a hydroxy group. But the functional group is an alcohol. And so we're first going to talk a little bit about how we classify alcohols, some of their properties in terms of their acid-base characteristics. Can we protonate them? Can we deprotonate them? And then we'll go on to how do you make alcohols, and then how we react them. So first of all, looking at an alcohol, these lone pairs make that alcohol a nucleophile. That's the source of electron richness. It also makes it a Lewis acid so that we can take an alcohol, and as we've done in the past, we can react this with an electrophile such as a proton. And that proton could come from something like HBr. That proton could also come from something like sulfuric acid. So in this case, the O could be the pair of electrons used to bond the H plus, and then the pair of electrons in either one of these cases goes to the bromine or goes to the oxygen. So that what we end up making is we end up making an oxonium ion. And we've seen oxonium ions in the past as either the result of a water attacking a carbocation or adding to a carbocation, or protonating the OH in the case of a dehydration reaction, which we will talk about as part of reactions of alcohols. So the oxygen then is electron rich, and so it can be a nucleophile. Now once we protonate that OH group, whether the water leaves or not is dependent upon what type of carbon the OH group was attached to, and now the oxonium ions attached to. So we classify this carbon as either primary, secondary, or tertiary. Remember, that's totally based on the number of carbons that are attached to that carbon. And if we had the case where we had, for instance, a secondary carbon or a tertiary carbon, and we were to protonate the alcohol to form the oxonium ion, then we could lose the water to form a stable carbocation. So we could end up with either a secondary or a tertiary carbocation. If it's a primary carbocation, number one, you're not allowed to draw that. But if this was a primary carbon, then we would have to basically do an SN2-like reaction or even an E2 reaction in order to lose the water and have the nucleophile either come in and attack that or lose a beta hydrogen in the case of an E2. And just to remember that when I classify reactions as one, that means they undergo a carbocation intermediate. If I classify something as a two mechanism, it means there's no carbocation intermediate. So I broaden the definitions of E1, E2, and SN1 and SN2 out. And we'll see examples of that as we go through the reactions of alcohols. So that's one of the characteristics of an alcohol, is the ability to protonate it with H+. So primary, secondary, and tertiary are based on the type of carbon that's attached to the OH group. There is also another type of alcohol that has special characteristics, and that's called a phenol. A phenol has the OH group attached to a benzene ring. Phenols historically were some of the first antiseptics that were developed. It was found that phenol itself could be used to prevent infections. The only problem with phenol is that it tends to be a little bit harsh in terms of its biological activity. So very rarely do we use phenol as a disinfectant now, but certainly compounds where there are different things off the ring can be used in that role as either an antiseptic in medicine or as a disinfectant. The advantage of phenols is that they are much more acidic, as we'll see in a moment, than a normal alcohol. So there are two ways that we can look at the alcohols. We can either look at their role in terms of gaining a proton, where they would act as a Bronsted base, or they'll act as a Bronsted acid in terms of losing a proton. And what we know is we know that the pKa of an alcohol is 16 to 18. And by reference, a pKa of water is 16. And just to remember, when you take an acid and you have it dissociate to form an H plus and an A minus, or probably more appropriately, if we were to react the HA with water and have that equilibrium between a hydronium ion and an A minus, then the Ka is the equilibrium constant for that acidity equilibrium, and the pKa then is minus the log of the Ka. So the larger the Ka, the smaller the pKa, or smaller the minus log of Ka. Now, one of the problems that you get into with acidity, measuring acidity or basicity of organic molecules, is the fact that most organic molecules are not soluble in water, and so you have to use solvents other than water in order to make the pKa or the Ka measurements. And you might say, but wait, I thought the pKa of water was like 14, because that's what the acidity scale is in water. And the answer is yes, in pure water, but when you put water in another organic solvent, you get a pKa of 16. Just as a sort of an aside, the solvent that has typically been used to measure the Kas and pKas of thousands of organic molecules has been this polar aprotic or polar non-hydroxylic solvents, dimethyl sulfoxide. And there's thousands of Ka and pKa values that were measured in DMSO by a group at Northwestern, Fred Bordwell's group. I made some of these measurements in my PhD thesis, and they're very tedious, and it's something that most times we don't really get into, but there is a huge difference in pKa's in non-water solvents and pKa's in water solvents, and that's why there's a discrepancy between water having a pK of 16 versus 14 in pure water, is because we've changed the solvent. But nonetheless, what happens is that the pKa of alcohol is a little bit weaker than it is of water. And just to give you and kind of review here a general idea, in Organic 1 you may have talked about the idea that just in this simplified equilibrium, the way that we make a stronger acid is to somehow push this equilibrium to the right. Now, you can't use Le Chatelier's principle to push the equilibrium to the right, because basically you could increase the amount of HA, but that wouldn't increase the overall percentage of dissociation. So one of the ways we push the equilibrium to the right is we make one of the products more stable. And if you make those products more stable, then the equilibrium pushes to the right. You get more dissociation of the acid, greater H plus, and a stronger acid. So one of the ways to make A minus stronger is maybe to use resonance, and we'll see that with the phenol group in a minute. But in general, the more stable I can make the conjugate base of an acid, the stronger the acid will be. Now, the converse is true, meaning that if you make the A minus less stable, you won't have as much dissociation, and that's what happens in an alcohol. So if you think about this, think about taking something like methanol and making the alkoxide out of it. So that's going to be our A minus. When I put an alkyl group on an atom with a negative charge, what I would really like to do is to take that negative charge and to distribute or delocalize it back into the alkyl group, but that's not the way it works. Remember that a tertiary carbocation is more stable than a secondary, more stable than a primary. Why? Because when you have an alkyl group, the hydrogen is slightly positive, and the carbon then becomes slightly negative at the expense of the hydrogens. And so this carbon being slightly negative can't accept any negative charge from the oxygen. As a matter of fact, it's trying to push negative charge into an already negative atom. And so this basically destabilizes or makes the A minus less stable, which means that our acid is going to be weaker, and that's exactly what happens in the case of an alcohol. So alcohols are weaker acids than water is because the alkyl group is not stabilizing the O minus. As a matter of fact, it's destabilizing it. Now, when we look at an O minus on the periodic table, remember that as we go from right to left, basicity on the periodic table increases. And so that means that a C minus, and at this point we're going to say an H minus and a C minus are comparable. Those are much stronger bases than an N minus, which is stronger than an O minus, which is stronger than an F minus. So in the Organic 1 course, we talked about the idea that horizontally basicity increases from right to left. Well, now what we have is now we have two levels of O minus. And so we should have that the RO minus is greater than hydroxide in terms of it acting as a base. So as we said here, this alkyl group destabilizes the O minus. When you destabilize something, you make it basically stronger. So a weaker acid over here would make a slightly stronger base. So alkoxide is a stronger base than hydroxide is. So you can deprotonate an alcohol, which we'll talk about in a moment, but predominantly these two reactions really don't occur to any great extent in water. But we can protonate an alcohol to make the oxonium ion, and we can deprotonate an alcohol to make the alkoxide. So the alkoxide we've already used as a base, for instance, right, our tertiary butoxide, and we will talk more about how to use something like ethoxide or methoxide, which in the first semester course we talked about being either a strong nucleophile or a strong base. And so we'll talk more about these two and expand on them as we go through. So alcohols must be deprotonated by stronger bases to make alkoxides. So if we go back to our periodic table here, what bases are stronger than an RO minus? N minus and C minus and H minus. Those are going to be our bases that are stronger than an alkoxide. So if you just use a hydroxide, you're going to get an equilibrium. And you're not really going to form much alkoxide, although at the end of this semester we will use this traditional way to make a little bit of alkoxide. But it's an equilibrium reaction. If you want to deprotonate the alcohol 100%, you need to use either an N minus, a C minus, or I will even throw in here an H minus. And we'll talk about where these come from as we go along here through the next couple of lecture videos. So NH2 minus was our small, strong base from E2 reactions. And so it will completely deprotonate an alcohol to form an O minus. We haven't talked necessarily about how to make a C minus yet, but when we do with Grignard reactions, they will completely deprotonate the alcohol. H minus, there's lots of sources of H minus. We have talked about using NaBH4, primarily NaBH4 when we were doing the mercuration. Remember, we could react a double bond. We could react a carbon-carbon double bond with mercury, water, and then we added sodium borohydride to that reagent, to that reaction. So sodium borohydride is a source of H minus, and we'll talk a little bit more about that. There's also a stronger source of H minus, which is called lithium aluminum hydride. Also, you can just actually buy potassium hydroxide or sodium hydroxide. So you can actually get the metal forms of those two hydrides. So any of these are a source of hydride that could be used to deprotonate the alcohol. So in general, how we form alkoxides is we react them with a strong base. Sodium, amide, C minus, or even an H minus, not an H plus, an H minus. Now, the much more traditional way of making an alkoxide is to react it directly in a redox reaction, meaning an oxidation-reduction reaction that you most likely learned about in general chemistry. So if you remember from general chemistry, if you reacted water with sodium metal, you end up forming hydroxide and sodium hydroxide with hydroxide and a sodium cation, and then molecular hydrogen or hydrogen gas. This is a redox reaction because the sodium is going in terms of oxidation number from 0 to +1, and the hydrogen is going from +1 to 0, being in its elemental form. So that reaction is quite spectacular. You can look at YouTube for all the sodium reactions, and none of them are very good in terms of safety, but sodium will react very readily with water. Well, remember that HOH is not that much different than ROH. Alcohols react very similarly to as water does because it's just there's an alkyl group on there. So if you take an alcohol and you react it with sodium metal, you'll make the alkoxide and hydrogen gas. And this could be even a more dangerous reaction because not only is the hydrogen gas flammable, and what normally sets a sodium metal and water on fire is the fact that the hydrogen gas gets ignited with the spark that comes off of the sodium reacting with water. Now what you have is you have flammable alcohol and flammable H2, and that's not really a good situation. So if you're going to make an alkoxide with sodium, or even worse yet, potassium, because it's more reactive, you have to be very, very careful, but it can be done. If we want to make our potassium tertiary butoxide that we used for our E2 reactions, the easiest way to do that is just simply to take tertiary butyl alcohol and react it with potassium metal carefully, and you'll get potassium tertiary butoxide. We've done this reaction in my lab. One of my first graduate students, we actually took not tertiary butoxide, but we took tertiary pentoxide, and we reacted it with cesium metal to make the cesium alkoxide. And cesium basically is infinitely more reactive than potassium. As a matter of fact, we did this when he first did this. He did it in a what's called a dry box, where you have basically it's like those little baby incubator things where you have the gloves, only it's filled with an inert atmosphere like argon. And when he cracked open the vial of cesium, it started to glow red because there was a little bit of extracurricular moisture in the box, and it dried it out really quickly. But you can make alkoxides this way, and this has actually been around since the 60s. It's a very traditional way of making alkoxides. So you can either make alkoxides from using a direct acid-base reaction with a strong base, or you can use a redox reaction with an alkali metal. You could also use the sodium hydride, or probably the better one would be potassium hydride. Both of those reagents will deprotonate the alcohol and make the alkoxide. So you can either make a sodium alkoxide or you could make a potassium alkoxide. And for our purposes in this class, the alkali metal identity isn't going to matter, but in real life it sometimes does. So that's how we can make the alkoxide using alcohols that have regular alkyl groups. Now, going back to the idea of phenols, with a phenol you have the OH group attached to the benzene ring. And with a phenol, you can actually just simply deprotonate that with hydroxide. Now that means that the phenol is a stronger acid than is a normal alcohol. Normal meaning just an alkyl group here. So it's very easy to make what is called a phenoxide. And you can make the phenoxide by simply reacting the phenol with hydroxide. Now the reason that a phenol is a much stronger acid, so this is going to be a stronger acid than a normal alkyl alcohol. The reason is because there are resonance structures that you can draw for the phenoxide. And if there are resonance structures that you can draw for it, which we will in a moment, that means that this conjugate base is more stable. And when we make the product more stable, that pushes the equilibrium to the right. More acid dissociates, or in this case, the acid reacts stronger, and so we end up with being able to form the phenoxide in 100% just using hydroxide. Now you can use all the other reagents as well, but phenols being stronger acids will easily be deprotonated by hydroxide. So again, going back, why is an alkoxide not as stable as, let's say, hydroxide? Because our alkyl group has a delta minus charge on the carbon, and trying to push some electron density into something that already has electron density is not particularly good. So when there are alkyl groups attached, that kind of pushes electron density in here. And that means basically that if we were thinking about the types of alcohols and whether they were stronger or weaker acids, what we would find is that every time I put an alkyl group on an alcohol, and now I'm not just talking about basically putting, a hydrogen on there, which is going to cause this carbon to become slightly negative. I'm talking about the alkyl group attached to that carbon. What it would mean is that in terms of acidity, a primary would be slightly more acidic than a secondary, which would be slightly more acidic than a tertiary in terms of the acidity of an alcohol. So tertiary alcohols are not going to be as acidic as primary alcohols, or even methanol itself if there were 3 hydrogens. That is a really small difference, but it is a trend. And it does make sense because every time I add an alkyl group to this carbon, I'm destabilizing it by pushing in electron density. So if we take a hydroxide ion, we could definitely deprotonate this phenol. And once we make the alkoxide, there are a number of resonance structures that we can draw. Now, to this point, we haven't really drawn the resonance structures of anions. Remember, we haven't even drawn the resonance structures of carbocations. So what happens when you have an anion is that I have this O minus. I have the 3 lone pairs on the oxygen, which gives it a negative charge. If I take one of those lone pairs and I use it to form a carbon-oxygen double bond, I've got to break this carbon-oxygen double bond and give that pair of electrons to this carbon. So I can form a double bond to that oxygen, but then this carbon now is going to pick up a pair of electrons and become negatively charged. Well, I could then take that pair of electrons and move it to form a double bond here, and then take this pair of electrons and give it to this carbon. So I can have the negative charge there. And in this case, the negative charge represents a pair of electrons. And then I can do that a third time. So in this case, what I have is I have 3 basically extra resonance structures. And those 3 extra resonance structures then cause this anion to be a little bit more stable than an alkyl alkoxide. And that pushes the equilibrium to the right, making the phenol a stronger acid. So that's why phenoxides can be formed with hydroxide as well as all the other strong bases. Okay. This is actually turns out to be important in the lab, because if I have a phenolic material and I would like to extract it, one of the things I can do is deprotonate it with hydroxide. And once I form that phenoxide, since it's ionic, it'll end up dissolving in the water layer. And so one of a typical organic experiment that sometimes we do is we will try and separate something like acetosalicylic acid, which is aspirin. This is the structure of aspirin, which is acetyl salicylic acid. So if you want to separate acetosalicylic acid from other components, let's say in an Excedrin tablet or something like that, what you can do is treat this with hydroxide. It'll turn it into an ionic substance. It'll dissolve into the aqueous layer, and then when you want to get it back, you just simply protonate the molecule. So this is acetosalicylic acid. You would deprotonate the carboxylic acid. If we had something like salicylic acid, which would be this phenolic compound, we could do the same thing. This is just salicylic acid. We'll talk a little bit more about that. The other sort of analgesic drug that you can have is this one, which this is acetaminophen. And acetaminophen as a phenol can also very easily be deprotonated by hydroxide. So you could separate the acetaminophen from other molecules simply by turning it into an ionic substance. So phenols are more acidic, and the difference there is they have additional resonance structures of the phenoxide of the O- anion, and therefore they can be deprotonated by a weaker base such as hydroxide. So that's a little bit of background on alcohols, and now we're going to put that background to use in the next few lecture videos as we look at their reactions. So the first thing that we're going to talk about here is we're going to do some review. And the review here would be, what reagents should we use to accomplish the syntheses of these different alcohols? And so, for instance, here are a couple of reactions, and what I would normally do is your pre-lab quiz or pre-lecture quiz, the online quiz would actually be to tell me what reagents you would use to convert this molecule into this one. And since this is the first lecture video of the second semester, I'm not going to, shock your system that way. But let's think about what kind of reaction this is. So what kinds of reactions do we know about? We know about substitution reactions, right? We know about elimination reactions. We know about oxidation reactions in terms of last semester's oxidative cleavage. And we also will know about reductions here at the end of this lecture, at this series of lecture videos. So of these three reactions, both of these fit one category of reaction. So if you're new to the lecture videos, what will happen in a moment is the lecture video will stop and you'll be asked a question on the screen. And so what you're going to do is you're going to answer that question. Now, I grade those based on participation, but it's a good test. It's a good way for me to see how people, what people know, what people are having problems with. So in a moment, the video is going to stop and it's going to say, what kind of reaction are these? Are they substitutions? Are they eliminations? Or are they oxidation reactions? So when the video stops, you can go ahead and answer that question. Remember, these are graded on participation. So, you're just going to give it your best educated guess if you don't know. Okay, so whenever you're looking at these kinds of reactions, let's take a look at what goes on. So elimination reactions do what? They tend to form carbon-carbon double bonds from last semester. Oxidation reactions tend to do what? You tend to either lose hydrogen or gain oxygen. Well, neither one of those fit in this case. What am I doing? I'm substituting OH for Br in both of these cases. That's what I'm doing. So these are substitution reactions. And for those of you that have some psychic abilities, you can probably guess the question that I'm going to ask now. My next question is going to be, what kind of substitution reaction is the top reaction? It's going to be an SN what reaction? Is it SN1 or is it SN2? So when the video stops here in a moment, go ahead and tell me, is it SN1 or is it SN2? Okay, what did you say? Well, since this is a primary halide forming a primary alcohol, this has to be SN2. Why? Because SN1 involves a carbocation. So this is an SN2 reaction. And then my next question would be, for this tertiary butyl bromide becoming tertiary butyl alcohol, what mechanism would it be? Again, it's going to be a substitution. SN reaction, is it SN1 or is it SN2? So go ahead and answer that question when it pops up on the screen. Okay, since this is a tertiary halide, can a tertiary halide undergo SN1? Yes. Can it undergo SN2? No, it can't. So this is an SN1 mechanism. Okay. Now, what's our overall goal here? Our overall goal here is for you to tell me what reagent I would use to convert propyl bromide into propyl alcohol. But knowing what the mechanism is really helpful, because that's going to tell me what reagent, that's going to tell me what reagent I should use. And so what reagent should I use if I want to replace a Br with an OH? And I'll give you two. We could use H2O, or we could use hydroxide, or we could use both, or we could use neither. So for the first reaction, what would you suggest? Should we use H2O, hydroxide? Both of them would work, or neither of them would work. Which reagent do you think would be the best, or which answer would be the best? Well, since this is an SN2 reaction, my primary halide has to react with what? It has to react with a strong nucleophile. What's the strong nucleophile? Hydroxide. So hydroxide would react with a primary halide to form the primary alcohol. So it would just be hydroxide. So what about the second reaction? What could I use? Could I use hydroxide only, water only, both, or neither for that reaction? What do you think about that reagent to give me that alcohol? Well, in this case, water definitely would work because being a tertiary halide, SN1 would be the mechanism, and water's a weak nucleophile, so it would be a good choice. Now, I would also say that hydroxide is okay, although the Top Hat textbook, in their more expanded chart, they tend to say if you react the tertiary halide with a, basically they classify hydroxide as a strong base, that you might get some E2 product, but I would use more or less our original chart from last semester, which says that a tertiary halide plus hydroxide would basically give me would give me an SN product, not an E product. So I would say that both hydroxide and water would be okay for this reaction. But the book would probably say only water would be appropriate because hydroxide would give me an E2 reaction. Again, these are kind of in the weeds, the gray area between SN1, SN2, E1, and E2. So I would say both of those would be okay. All right, so let's continue. Let's talk about how would I convert this double bond into an alcohol. And these are review questions because we always, whenever we talk about making a functional group, we always do some review. So we say, what reactions do we know that can be used to make that functional group? And then we learn new ones. So we're still in kind of the review process. So what reagents could I use to add basically an H and an OH across the double bond? Well, I could use H plus H2O. What else could I use? I could use Hg acetate, mercury acetate, water, and then sodium borohydride. That's mercuration, demercuration from last class. What else could I use? BH3, H2O2. What's that? Hydroboration oxidation. Any other reagents I could use to add an H and an OH across the double bond? I think that's it. So, what reagent or reagents can I use in this reaction to make this molecule? And I'll give you some choices. We'll say A, B, and C. So A only, B only, C only. And then another choice would be A and B only, A and C only, B and C only, or all three. So when the video stops here in a moment, what would be your choice of converting this double bond into this alcohol? Okay, so the next question after we said we added an H and an OH across the double bond is, how did we add it? We added it by Markovnikov's rule, right? The hydrogen that had the hydrogen gets the hydrogen. So it's Markovnikov addition. So what reagents would those be? They would be both A and B, because just simply hydration of H plus H2O and mercuration demercuration gives Markovnikov addition. So A or B could be used to get this product. Okay. So now let's look at the next one. I added H and OH across the double bond again. Same question. What reagent or reagents can I use to convert this methyl cyclohexene into this molecule? Okay, so when the video stops, go ahead and give me that answer. Okay, so I added H and OH how? Anti-Markovnikov. The H added to the carbon with the least number of hydrogens, the OH added to the carbon with the most number of hydrogens. So it's anti-Markovnikov addition, which would be hydroboration oxidation. And remember, hydroboration oxidation also adds H and OH 100% cis. Okay, oh, we have more. Only now what we have is adding two OHs across the double bond. So what reagents could I use to add two OHs cis to the double bond? Well, from the last class, last semester, you could use KMnO4 and hydroxide. What else could I use? I could use osmium tetroxide and hydrogen peroxide. Both of those did cis hydroxylation. What if I wanted to add two OHs trans from the double bond? Well, there's a hint down here that says I need two steps. So the two steps that I need is I need to convert this double bond into an epoxide, and then open up that epoxide to form the trans dialcohol. So once you have an epoxide, you can open it up with H plus H2O. How did I make the epoxide originally? I either used a peroxy acid, like MCPBA would be a specific reagent. I could also react the double bond with bromine and water. Or, well, and followed by hydroxide. So I need to make an epoxide and then use hydrolysis, acid hydrolysis, in order to make the trans dialcohol. Okay. These reactions are a little bit more difficult for me to put in a multiple choice format to have you do it, to stop the video and have you do as a quiz. So those are our review syntheses of alcohols, and it's important to remember those because when we're talking about alcohols, the first question is, how can I make them? And those reactions we've already talked about. Now let's talk about some new ones. And the new ones are all going to be based on carbanions. And a carbanion is a carbon with a negative charge, which means that carbon has a lone pair of electrons to give it a -1 formal charge. So carbanions are made from alkyl halides. And we'll talk about how we do that in a minute. But we're used to talking about carbocations where the carbon has a slightly positive charge. So this is going to be changing the carbon from being an electrophile to being now not only a nucleophile, but also what goes with that with C- is it's not only a nucleophile, but it's a strong base. The carbanion has to have a counterion, which in this case will either be lithium or magnesium. Those are the counterions for the carbanion. And in the real world, that the anion makes a huge difference. But in this class, we're going to treat whether we make this with a lithium or magnesium, or even a copper later on, as being basically the same, and they're really not. And I could go on a lot about that because that was the area of my PhD work. So what we're going to do is we're going to make a C-. Now, how do we make a C-? What we do is we take an alkyl halide and we react it with 2 equivalents of a metal, or just 1 equivalent of magnesium. So we end up forming our carbanion with our metal counterion. So let me just write out the 2 possible reactions, and let me just take something like methyl bromide would react with 2 lithium metal atoms, and what it would form is CH3- Li+, and then the balanced equation would be another lithium plus and the Br-. Whenever the counterion is lithium, that is called an organolithium reagent. And you need 2 equivalents of lithium to react with 1 equivalent of the halide. Now, in my notes and in homework problems and practice problems, you're going to see that I don't necessarily always take the time to balance this equation out, even though I should. So if you just see me reacting an alkyl halide with a lithium, then I'm basically making the carbanion. And sometimes I'll leave the lithium out because I'm focusing more on the carbanion as opposed to having the counterion. But in the real world, this C- cannot exist without a counterion. Okay, and the counterion does make a difference, whether it's lithium, sodium, potassium, or magnesium. So the other way to do this would be to take that CH3Br and react it with 1 equivalent of magnesium. And in that process, I would be making my CH3-, and my counterion would now be an MgBr. The magnesium has a 2+ ionic state, and Br with a -1. So the net result is the MgBr has a +1 charge. So that kind of is the counterion, whereas up here it's just a single metal atom, metal ion, the lithium. So that's kind of the difference between an MgBr plus and a lithium plus. MgBr is called the Grignard reagent. It's called a Grignard reagent, and was discovered by Victor Grignard, that you'll see in a minute. So both of these are classical ways to make carbanions. And once we make that carbanion, we're going to be able to use that as a strong nucleophile. But remember, strong nucleophiles that are also strong bases can kind of go both ways. They can react as either a strong nucleophile or a strong base. And remember, on our periodic table, we go CNOF, and C- is the strongest base in that row. So we can use organolithium reagents, we can use Grignards. We're going to focus more on Grignards, but organolithiums are equally valid. And one of the most popular organolithium reagents is what's called butyl lithium, where there's a CH2- on a butyl group and a lithium plus. That is used both as a nucleophile. It's used a lot to make rubber. Like Goodyear uses a ton of this to make the rubber that goes into tires. And this can also be used as a strong base to deprotonate things. It's one of my favorite molecules, I think, as a postdoc, and being here at John Carroll, we've published a number of papers where we've determined the structures of butyl lithium both in solution as well as if we can get little crystals of them. And so it's one of my favorite molecules. So Victor Grignard made Grignard reagents and will be forever known in organic chemistry for his reagents. Although, to be honest, he borrowed some of the work of Barbier, who did some work with sodium and potassium. So a lot of the work in the late 1800s, early 1900s in sort of carbanion chemistry is very historic and not necessarily well known by even the people that work within that area. So let's talk a little bit about using these C minuses. So these are typically called organometallic reagents because they have metals as counterions to organic materials. They can be nucleophiles or they can be bases. So you can react the R minus with an electrophile, some type of electrophile, to form basically a bond, or you can use them to deprotonate an acid to basically make nothing, to basically make your A minus. And so whenever we're using these organometallic reagents, whether it's an organolithium reagent or it's a Grignard reagent with the MgBr+, we have to keep these away from any molecules that have acidic hydrogens or they will deprotonate them. The most relevant is water. It'll also deprotonate an NH, and it'll also deprotonate a carboxylic acid proton. That means that whenever you work with these reagents, you have to exclude moisture from the atmosphere as well as from the glass. So whenever we're doing this reaction, we usually have to bake our glassware out in the oven, or we have to flame it to remove all the water that's absorbed to the surface of the glassware. And when we do the reactions, we have to do them usually under an atmosphere that doesn't have any water in it. Sometimes we use argon or purified nitrogen gas that has all the water removed, because these two compounds will simply deprotonate water, and we will turn our R minus into an alkane, which isn't going to be helpful. On the other hand, sometimes we do want to use these molecules to do deprotonations. So the advantages of using these types of organometallics is that it is very easy to convert the carbon that's attached to the halogen into a C minus, and any carbon can be used, even a carbon attached to a double bond. So if you wanted to turn a benzene ring into a C minus, you would just react this benzene ring with this benzyl bromide or bromobenzene with lithium metal, and you can make the carbanion. It's very difficult to deprotonate the CH of a benzene ring. Something like N-butyl lithium, which was our CH3, CH2, CH2, CH2 minus, Li plus from the last slide, that actually will only deprotonate this hydrogen in certain circumstances. And this N is currently not in vogue with the naming people. So it's very difficult. This is sort of an ineffective way of making this C minus, whereas we can react any alkyl halide with lithium metal and make that organolithium reagent. So we could either use magnesium or lithium to make this C minus. So that's how we're going to do it. We're not going to use deprotonation reactions, although it is possible to deprotonate this hydrogen, but not using the reagents that we're going to talk about in this class. Okay, so what do you do when you have a C minus? And once I have a C minus, let's say I make my CH3 minus with my MgBr plus. What I'm going to primarily do is react those with carbonyls. So this is kind of a review. We did this once before in Organic 1, and that was that we took an alkynyl anion and we reacted it with a carbonyl group, where the C minus would then come in and attack the carbon of the carbonyl and then break the CO bond and give that pair of electrons to the oxygen. And what we ended up doing then was we ended up forming an O minus, and then we had our C triple bond C. So we in this case made a carbon-carbon bond. So if I'm going to make so that is only for alkynyl anions. And how did we make the alkynyl anion? We took advantage of the fact that a terminal alkyne could be deprotonated with something like NH2 minus in order to make the C minus. But now that I know how to make a Grignard or to make an organolithium compound, what I can do is I can do that same reaction. So my CH3 minus in this case, let's just go ahead and replace this with a CH3 minus. My CH3 minus would come in and attack this carbon because that carbon is delta positive, so nucleophile, electrophile. Then if I form a carbon CH3 bond, I've got to break the CO bond and give the pair of electrons to the oxygen, which is perfectly fine because that's the way the bond is polarized. Then over here I would have my CH3 being formed, and I would form my alkoxide intermediate. So in these reactions, I'm going to add my Grignard reagent to my carbonyl and make the alkoxide. In the lab, what I do is I do this reaction. And then once the reaction is over, I need to convert the alkoxide to the alcohol. And the way that I convert the alkoxide to the alcohol is just simply adding an acid. So typically these reactions are set up so that I would say I'm going to react CH3 minus MgBr plus with something like acetone. And then I always say then H plus. Or sometimes you'll see then H plus H2O. So we react the Grignard first with the carbonyl, and then we add H plus to it. So these are two distinctively different steps. If the acid was present while the Grignard was present, it would just simply protonate the Grignard and the reaction would never go. So in this case, what I would end up doing is I would end up forming that alcohol by adding the methyl group to the carbon that was originally the carbonyl. Now, this reaction of reacting a nucleophile with a carbonyl is general, and we'll spend a good chunk of time this semester talking about that with all different types of carbonyls. Carboxylic acids, aldehydes, esters, ketones, and other carboxylic acid, what we call derivatives. In this case, we're going to focus on this reaction being an aldehyde or a ketone first. Then we'll talk a little bit about carboxylic acids and what are called acid chlorides and esters. So this is our overall reaction of any Grignard or organolithium reagent. Okay, so I could react any Grignard with a carbonyl. So let's say I reacted it with something like CH3, CH2, C double bond O, H. So let's react this with an aldehyde. And then add H plus in the second step. So what's going to happen? The C minus is going to come in and attack the carbonyl, and the pair of electrons will go up here. I'll add a CH2, CH3 group here, and I will make the O minus. Now, the counter ion to that O minus is an MgBr plus, but we normally don't show that. And then I add my H plus step, which means my O minus comes and reacts with the H plus, and I form my final product. And I'm going to write this CH2, CH3 group in a line. So in this case, reacting a Grignard with an aldehyde gives me a secondary alcohol. And so the reason we're talking about Grignards is because when you react them with carbonyls, you end up forming alcohols. So these are new reactions to synthesize alcohols. Okay. So we can look at all of the possible types of carbonyls and see what type of alcohol we make. So for instance, if you react a Grignard or an organolithium compound, and that's what this means, if you react that with a carbonyl, with a ketone where there's two alkyl groups here, and I'm using R and R prime to indicate that they could be the same, they could be different. If I react that with this R minus, with this Grignard reagent, what I end up doing is adding that R group to the carbon and make an alkoxide, and then the alkoxide again gets protonated to form the final alcohol. So if you react a Grignard or an organolithium compound with a ketone, you end up forming a tertiary alcohol where two of the groups came from the ketone and the third group came from the Grignard. And we'll talk about thinking about this reaction in reverse here in a few minutes. If you want to make a secondary alcohol, as we saw, react your Grignard with your aldehyde. That alkyl group, that carbanion will add to the carbonyl, and then you'll protonate it with H plus to give you the secondary alcohol. So if you want to make a secondary alcohol, it's Grignard plus aldehyde. And then if you want to make a primary alcohol, what you need is you need basically a carbonyl that has two H's on it. This is called formaldehyde. And so again, the R minus would come in, attack the carbonyl, and now I would add my alkyl group to my carbon that now has two H's on it, and then when I add my H plus, I end up forming the primary alcohol. So in each one of these reactions, by using a ketone, an aldehyde, or formaldehyde, I can form a primary, secondary, or tertiary alcohol. I could also react this Grignard with carbon dioxide, right, CO2. And when I react the Grignard with carbon dioxide, the C minus attacks the carbon, and then it breaks one of the two CO double bonds and gives a pair of electrons to the oxygen. So what I ended up doing was adding the R group to the carbon. One carbonyl, the carbonyl group, one CO double bond stays intact, forming the carbonyl group, and then we get an O minus. And then when I add the H plus, I end up forming a carboxylic acid. So it's also possible to basically add a CO2H group to an alkyl group by using a Grignard reaction. And that's a fairly useful reaction. We've done that in the lab when we've made long chain carbanions and we want to put a carboxylic acid group on the end. We just simply added a little CO2 to it. Okay. So there's lots of ways you can do this reaction. And what I'm showing you is sort of the forward reaction, but then what our product is that we get out. So some examples. Some examples might be, let's say I wanted to react the cyclohexyl bromide with magnesium metal. I would end up converting that carbon to a carbanion with the MgBr plus counterion. And let's say that I reacted that with something like this ketone. This would be butan 2-one would be its name. So the C- of the cyclohexane ring would attack the carbon. We would end up with adding that to the carbon. It would have a CH3 group on this side, a CH2 CH3 group there with the O-. And you don't always have to write the MgBr with this. And then you would add H+ to this, and you would end up then forming this alcohol where you have a methyl group, an ethyl group, our cyclohexyl group on that alcohol. So that would be one example of doing a Grignard. Another example would be, let's say we take a cyclohexyl group, but now we take our bromine in this position, and we now add magnesium metal to that. We would end up with this carbanion, and let's say I wanted to react that with CO2. CO2 would have the O double bonded to C, double bonded to O. So now that C- would come in, add to that carbon, and we would end up having a C double bond O-. That's a deprotonated carboxylic acid, and then we would add H+ to it to then give me the final product. So I could go ahead and add the carboxylic acid group to the original alkyl halide. Okay. So in all these cases, what I'm doing is I'm ending, two of the three groups were in the original molecule. And then I'm adding a third alkyl group to form a carbon-carbon bond. And at this point, I should take a minute and just say that in organic chemistry, particularly in the late 1800s, early 1900s, the premium reactions, the most important reactions, were always the ones where you formed a carbon-carbon bond. So most of the reactions where we do form a carbon-carbon bond are given names. The person that discovered them or the person that was given credit for them is always cited. So for instance, the importance of the Grignard reaction is the fact that I can form a carbon-carbon bond, and I also then form an alcohol. And then the overall scheme of organic chemistry then, the idea is to basically take a carbon skeleton and add functional groups to it and convert those functional groups into other molecules. So in this case, I'm forming a carbon-carbon bond, and I'm basically having an alcohol that I could do what with? I could replace it with a halogen. I could form a carbon-carbon double bond by doing dehydration on this alcohol. and all of the other reactions that we're going to talk about with alcohols. So that's how we can, that's the importance of sort of synthetic organic chemistry, is building up molecules, and the premium has always been forming carbon-carbon bonds. Okay. Now, I have to note, in both these cases, I've made those bonds sort of dark. Let me just go back and change them, because if you're saying, are those bold wedges? No, they're not bold wedges. As a matter of fact, even if we were to make a chiral center out of this molecule, the carbonyl isn't chiral to begin with, so the O- could add from, it basically could add from underneath or above the plane in terms of adding to the carbonyl, so we would get a racemic mixture. In organic chemistry, in order to make a chiral molecule, one enantiomer over another, you need to have a chiral reagent. In this case, we don't. So that would be our... So I don't want to leave the impression that there's stereochemistry here, because there is not. Okay, so then let's take a step back and think about the reverse. Think about backwards thinking. And usually at this point, everybody's like, I have enough trouble keeping track of the reactions going in the forward direction. Let's skip going backwards. And I'm like, well, no, let's talk a little bit about that. So let's say that you wanted to make this alcohol. And I said, give me a method to make this alcohol from a Grignard. Well, how would you go about thinking about that reaction? And what I would say is that the carbon that's attached to the OH, what was it to begin with? What was it to begin with? It was a carbonyl, right? And what did I do? I added one of these three groups to the carbon that already had the other two groups present. So there's actually, in this case, there's two different ways to do this reaction. The first way might be to say, okay, let's choose two of these three groups to put on the carbonyl to begin with. So maybe I have the two ethyl groups on the carbonyl to begin with, and what was my Grignard? My Grignard was that carbanion with the C- MgBr plus. So the C- comes in and adds here. To give me that alkoxide, and then what would I do? Then I would do my H plus H2O step to give me the alcohol. And again, I've drawn a little bit different. Okay, the benzene ring is down here instead of over here. It's fine. It's all the same. So how else could I do this reaction? Well, I could say, well, what would happen if the benzene ring was already attached to the carbonyl along with one of the two ethyl groups? Okay, great. Then what would be my Grignard? My Grignard would be that. And so what would happen? That C- would attack the carbonyl, pair of electrons would go up here, and what would I end up making? I would end up making that alkoxide, and then add H plus H2O. So the idea here is if you were given an alcohol and said, how do I make that? Then what you would do is you would look at the groups that are attached to the carbon, and two of those groups have to be attached originally to the carbonyl, And then one of the other groups could then be the Grignard, and in this case, the Grignard could either be a CH3CH2 minus group, or it could be a benzene ring minus group. And this would be what is called a phenyl group, because when a benzene ring is a substituent, it's called a phenyl. Okay, so if there were 3 different groups attached to that carbon, there's 3 different ways to make that alcohol. So just a way to think about how to work backwards. I want to make this molecule. How would I do it? We started this lecture by talking about what reagents would I use to make those alcohols. That in a way is backwards thinking as well. So you kind of have to think about how one would do that. Okay? So that's just another way that we have to think about Grignard reactions. How do I make a particular molecule from a Grignard? Okay? Okay, so this isn't the only carbonyl. Aldehydes and ketones and carboxylic and CO2 are not the only carbonyl groups that we can add to a Grignard. We can also add an ester molecule to a Grignard. But if we do that, I'm going to end up with a different mechanism. Not only am I going to end up with a different mechanism, but I'm going to end up with actually adding 2 of the same alkyl groups from the Grignard to make a tertiary alcohol. And so we have to talk about this mechanism because it's a little bit different. And here's what happens. What happens is the R- comes in and attacks the carbonyl in the normal way. And I'm going to say this over and over again this semester in this class, and that is that whenever you add a nucleophile to a carbonyl and form the alkoxide, that O- always wants to reform a carbon-oxygen double bond. It always wants to do that because carbon-oxygen double bonds are so stable. So if I give this molecule human characteristics, whenever you form an O- by adding a nucleophile, it's always going to want to bring that pair of electrons back down and reform the carbonyl to become stable. But the only way that can happen is if something can leave. So let's remind ourselves about leaving group ability. And this would be a good place if I could ask a sort of a written question in the lecture video, but I can't. I have to make it multiple choice. So we won't do that in this point, but let me ask you a question. If you need to, stop the video and think about it. Last semester, when we talked about what makes a good leaving group, leaving group ability is based on what? Basicity. Leaving group ability is based on basicity. How? Directly or indirectly? Indirectly, I said last semester, inversely. So it is an indirect relationship between basicity and leaving group ability. Okay. Now, I'm setting the stage for the entire semester here. In our periodic table where we have C, N, O, F. C minus was our strongest base, and we're going to equate H minus with C minus. Then N minus, then O minus, then F minus. So which one of these is the strongest base? Okay, that's a review question, but the video will stop and you can go ahead and answer that. Of that series, which one is the strongest base? It's the C minus H minus, right? So which one of these groups is going to be the worst leaving group? C and H minus. They're going to basically not be leaving groups because they are such strong bases. N minus we can make leave, O minuses we can make leave as well. But for the most part, C and H minus, well, for all parts, they will never leave. And again, let me kind of put this in perspective. Organic chemistry is really about having a carbon-hydrogen skeleton and hanging functional groups off of it and changing those functional groups from one to the other and now joining groups together. That's what organic chemistry is really about. That's the power of it. That allows you to synthesize drugs, that allows you to synthesize new materials. That's what organic chemistry is. You have a carbon-hydrogen skeleton with functional groups hanging off of it. Okay? So, it would be utter chaos if your skeleton could just leave, could act as a leaving group. So, I don't know if it's coincidence, but to have the carbon hydrogens being the worst leaving group is perfectly consistent with that idea that that's the skeleton and that's not going to change very much. Yes, we can cleave carbon bonds. Yes, we can cleave carbon-hydrogen bonds, but those are not, the majority of the reactions that we do. Normally, we're just changing functional groups. So having carbon and hydrogen being your worst, or in this case, never leaving groups, they never act as a leaving group, kind of makes sense. So those groups will never leave. So when we were reacting, just to kind of tie this back to where we were, when we were reacting ketones and aldehydes with a Grignard, they already started out with groups that were never going to leave, and we're adding a group that once it adds isn't going to leave either. But now look at what I did. Now I put an OR group on there. So what happens is that when you add your Grignard and form your alkoxide, again, the O minus says, you know what, I can be more stable if I can bring this pair of electrons down. Is there a group here that can leave? Yes. The OR group could leave as an OR minus, and then I could reform my carbonyl. If that happens, I end up forming the ketone. Well, we already know that ketones react with Grignards to form now tertiary alcohols. So what happens when we react a Grignard with an ester is this. If I just reacted one equivalent of Grignard with an ester, I would end up with an assortment of products. Because if the Grignard react with the ester to form the ketone, then another Grignard would react with the ketone, and so I'd end up with a whole mess of products because then I'd be short on Grignard, and I'd end up with some unreacted ester, but I would end up with some ketone, and then I would end up with some tertiary alcohol. So what we do is just say, let's add 2 equivalents of Grignard. So when we add 2 equivalents of Grignard, what happens is we add the first equivalent, the OR group leaves, we reform the carbonyl to form the ketone, then the R minus comes in, attacks the carbonyl, and we form the tertiary alcohol, where now 2 of the R groups have come from the original Grignard. And then at this point, the O minus is trying to bring the pair of electrons, but nothing's leaving. So it's just stuck, it hangs out, chills, as the youngsters would say, and then the H, and I don't even know if that's current terminology or not, but I do my best to try and be a hip, cool professor. Then the O minus attaches the H plus to it, and we form the final product. So in this case, with an ester, I'm going to add 2 equivalents of Grignard. And I'm going to form a tertiary alcohol with 2 groups added. Okay, so that's the difference in mechanism. Whenever we have a potential leaving group here, it will leave and reform the carbonyl. And that's going to be the case throughout the semester. So I'm going to say that over and over again. Remember, when a nucleophile attacks the carbonyl and you form that O-, what does that O- try and do? It tries to reform the carbonyl. In this case, it can. Okay, so it's a different mechanism. We can also do that same reaction with what are called carboxylic acid chlorides. So let's take 2 equivalents of methyl Grignard here, and let's react it with, specifically, let's react it with this carboxylic acid chloride. So a carboxylic acid chloride has a chlorine atom attached to the carbonyl. And we'll talk about these molecules later on in the semester. But a carboxylic acid chloride is going to react with 2 equivalents of Grignard. So the CH3-, the first equivalent, is going to come in, add to the carbonyl, and form the alkoxide. Okay, now in this case, this O- would like to bring its pair of electrons back down and reform the carbonyl. Is there a group that'll leave? Oh yeah, chloride will leave all day. So I'm going to kick the chlorine off, and I'm going to reform my carbonyl, which means I'm going to form this Grignard. And I'm going to end up with a Cl-. Then what happens? Then my second equivalent of Grignard now comes in and adds to the carbonyl. Now I'm going to end up with my O-, and now I'm going to add my second methyl group to this molecule. And now the O- tries to bring the pair of electrons back down, but there's nothing that can leave. So now it just waits for the H+ to come into play. Waits to be protonated, which it is. And so I form my tertiary alcohol. Now my tertiary alcohol has the 2 methyl groups attached to it because 2 Grignards added to the original acid chloride. So these are slightly different mechanisms, but it introduces the idea that when you add a nucleophile to a carbonyl, that O- will want to reform the carbonyl always, but it can only do it if there's a leaving group present. Okay, so that's acid chlorides and Grignards. What else can I do with Grignards? I can add them to epoxides. So we have our CH3-, which is again going to be our strong nucleophile. And now we have our epoxide. So now we have to go back to last semester and remember about epoxide ring opening. Except that last semester when we opened up an epoxide, we did it by reacting it with H+ first and forming the oxonium ion, which then distributed the charge so that really what we were looking at was this. The carbon's taking on the brunt of that charge. There's a little bit of residual charge on the oxygen, but for the most part, the carbons took on the brunt of that charge. And these even could be thought of as being sort of partial bonds. What did that mean? That means that when the nucleophile came in, and we were using last semester, we were using either water or we were also using a halogen after the halogen, in like HX, where the H plus would protonate the epoxide to begin with, remember there was a positive 1 charge that was being shared by those 2 carbons, and our nucleophile would always add to the carbon with the greatest charge, the greatest delta positive charge, which means that the nucleophile always added to the carbon that was most substituted. Okay, now the reason I review this is because now I'm going to react this with a strong nucleophile that has a negative charge that's going to be able to come in and directly attack the epoxide and open it up. It doesn't need help. Water, and to some extent the halogen, needs help. It needs to be the epoxide to be protonated to put more delta positive charge on these 2 carbons to allow the water and the halide to actually open up the epoxide and attack those 2 carbons. In this case, this is a strong enough nucleophile to directly attack those carbons. So the first thing was that the stereochemistry that we did before was the water or the X minus always added from underneath, right? So it always added so that that group and the OH group were trans. Same thing's going to be true here. The CH3 minus, in this case, the Grignard is going to react from underneath, so that we'll end up with the added CH3 group and the OH group that's going to result being trans. But the question is, which carbon, A or carbon B, is the CH3 going to add to? Just out of curiosity, tell me which one you think it'll add to. A, B, or both? And when that question comes up on the screen, you can go ahead and answer it. I'm just curious as to what you think. Okay, so we've got a strong nucleophile reacting, and so I'm going to classify this mechanism as SN2. In other words, strong nucleophile direct attack on the carbon. Down here, you could think of this having an SN1 characteristic because it was the nucleophile was adding to the carbon that was most substituted, which means the carbon with the most charge. That looked more SN1-ish than it did SN2-ish. This is going to be straight up SN2. So SN2 means what? What kinds of halides react the fastest in SN2? Primary reacts faster than secondary, right? Tertiaries didn't undergo SN2. So which carbon is this strong nucleophile going to attack to? Attack the one that is least hindered. That's B. And so it'll do that. So now what we're doing is now we're opening up epoxides with strong nucleophiles. And we're going to talk more about this in the next lecture video, but in general, these reactions are sometimes called basic or base. Sometimes they're called base catalyzed, which is really kind of a misnomer. Base catalyzed is not what these are. These are strong nucleophile epoxide ring openings. And whenever you do a strong nucleophile, which means it has a negative charge, which means no acid, you're always going to have the nucleophile attack the least hindered carbon. And so what does that mean? That means that when CH3 minus attacks carbon B, and I break the CO bond and the pair of electrons moves up here, so I form an O minus, and then I've added my CH3 down here. That O minus does what? Waits for a then H plus step, and so then the alkoxide gets protonated and forms the alcohol. So in this case, we can open up an epoxide with a Grignard reagent but the regiochemistry changes from down here where it was acid catalyzed, which is also a misnomer, but it changed from the acid catalyzed reaction to, in essence, a strong nucleophile ring opening. And so those two have different regiochemistries. The acid catalyzed, the nucleophile adds to the most substituted carbon. In strong nucleophile ring opening, the nucleophile adds to the least substituted. Now I'm going to point something out here as well that is important to kind of see. And that is, if we go back and we look at any of the Grignards that we did with carbonyls, our Grignard alkyl group always ended up attached to the carbon that was the carbonyl group in the reaction. That's how the Grignards, that's what the Grignard alkyl groups were always attached to. When you react a Grignard with an epoxide, notice that the Grignard alkyl group ends up one carbon away from the carbon with the OH. And you can kind of see that these two carbons were the carbons involved in the epoxide. So the CH3 minus comes in and adds to the least hindered. So if you're looking at a molecule, you could now think about making a particular alcohol from an epoxide if you want to add the alkyl group not to the carbon with the OH, but to add the alkyl group to the carbon next to the carbon with the OH. And so that's how you can tell the difference between whether a Grignard's reacted with an epoxide or whether it's reacted with a carbonyl, is where it ends up relative to the COH group. Okay, so we'll talk about this more. That's strong, I call it strong nucleophile epoxide ring opening. Okay, a couple of sort of unintended side reactions of Grignards, or of any C minus. And one of those has to do with replacing a hydrogen with a deuterium atom. So in your textbook, you'll see Ds. And you go to the periodic table and you're like, wait, there's no D. Right, there's no D. D stands for the isotope of hydrogen that has a mass of 2, which is called deuterium. Deuterium is an important isotope to substitute for hydrogen in different molecules because it has a lot of uses. We'll talk a little bit about this in the lab class with NMR, but also the deuterium can be used because it has an extra adds an extra 1 atomic mass unit to a molecular weight. It's sometimes used in a technique called mass spectrometry. It also can be used to study reactions and also kinetics. But I won't get into that too much, other than to say this, that if somebody was interested in, for instance, making a butane molecule where they substituted one of the CH3 hydrogens with a deuterium, they could do that by making the Grignard and then reacting it with D2O, which is the equivalent of H2O. D2O is called heavy water. That's what's used in nuclear reactors. So D2O, the C minus would deprotonate the water and replace a hydrogen with a deuterium. So you could take 1-bromopropane and react it with magnesium to make the Grignard. Normally, reacting a Grignard with water would be a bad idea, but in this case, reacting it with D2O just simply causes the hydrogen to be replaced with deuterium, and so sometimes that's done. So this would be Normally we don't want to, what I call, quench the Grignard with water. But in this case, if that's our intent, is to replace a hydrogen with a deuterium, we could certainly do that. The other reaction that we will talk about in a little bit, we'll talk about modification of this in one of the following lecture videos, is the following. It's called Wirtz coupling. And basically what you have to think about is that when we have our carbon-bromine bond, that we're reacting with something like lithium metal. This could be done with sodium metal as well, but let's go back and talk traditional lithium. The lithium has one unpaired electron in its metal form. So this reaction is what is sometimes called a single electron transfer reaction. And single electron transfer, which are called SETs, are somewhere in between the movement of a full pair of electrons, right, where we show a full arrow. And those are our SN1 or SN2 reactions, and moving one electron with our fishhook arrow from free radical reactions. SET is kind of in between. So in this single electron transfer, what happens is we have two lithium metals, each having one unpaired electron. Now what's going to happen is both of those lithiums are going to give up their unpaired electron, so that I'm going to end up with two lithium plus ions, cations. And what's going to happen then is when I break the carbon-bromine bond, I'm going to end up having the bromine pair up with one of those unpaired electrons of lithium, and the carbon will pair up with the other unpaired electron of lithium, so that what I end up forming is the R has a lone pair and a negative charge, and the Br has lone pair with a negative charge. So the movement of these electrons is basically one at a time, which is what's called a single electron transfer. So these reactions can have some radical type characteristics, is I guess my point. So what was found was that if we basically reacted a organolithium or a Grignard reagent with alkyl halide, we would get a little bit of the coupling product. So the coupling product is when we bring basically two alkyl groups together to form a carbon-carbon bond. Last semester with the free radical halogenations, the coupling reaction was the third termination step in free radical halogenation. So that's where this terminology comes from. Well, we see a lot of Wirtz coupling if we perform a Grignard reaction incorrectly. And what do I mean by that? Well, when we're doing a Grignard reaction, we have to make the Grignard first. And so what we would do is react the alkyl halide with magnesium metal. And the problem is if we react this too fast, if we dump all of the alkyl bromide into the magnesium, what happens is that we will make some Grignard, but we will also have some unreacted alkyl bromide present. And those tend to undergo this Wirtz coupling reaction to make, in this case, this molecule called biphenyl. And so when we do a Grignard reaction, we have to add the alkyl halide slowly to the magnesium metal to make sure that we don't have a lot of excess alkyl halide present, or else we'll get a lot of Wirtz coupling products. So this is a side reaction of making a Grignard. Now, if you remember what I said earlier about in the 18 and 1900s, if you wanted to become famous so that every organic student forever on had to learn your name, make a carbon-carbon bond, you would jump at this and you would say, this is a great way to make make a carbon-carbon bond. Yeah, no, it really isn't. It makes a side product, but it doesn't make it 100%. So this is actually a pretty poor method to make carbon-carbon bonds, except when you don't want to, then you can make a lot of the Wurtz coupling product. So there are other ways that we can use organolithium reagents in particular to do carbon-carbon bond formation. They don't fit SN2 and they don't fit free radical. They fit this SET type mechanism, which in graduate school I hated because it always just complicated things. So if you wanted to take a Grignard and add an ethyl group to it by using Wurtz coupling, that wouldn't work very well. So let me give you a foreshadowing into some of the organometallic reagents that we're going to talk about in an upcoming series of lectures. And that is that I said earlier that the anion or the cation for the carbanion didn't really make a whole lot of difference. Well, I also said it didn't make a whole lot of difference in this class. In real life, it does. So if you wanted to make a carbon-carbon bond from an organolithium reagent, there's actually a really cool way of doing that. And that is to use what are called organocuprate reagents, or this is also called a Gilman reagent. And what you can do is, if you react your organolithium compound with a copper halide, this is a copper +1 species, not the normal copper +2 that we look at. What we end up doing is we end up actually combining two anions and a copper +1 and a lithium +1. And that structure is called a Gilman reagent, but it essentially has a carbanion sort of like Grignard reagent. But these reagents, because copper is a mess, and I've have some projects that are unfinished where we were trying to do some reactions or trying to make precursors to copper molecules, and copper's all over the place. It forms different colors. It can form a paramagnetic species where it has an unpaired electron. I mean, it's just a nightmare to work with. And I guess that means that it's super interesting if that's what you're interested in. So this Gilman reagent, or this lithium cuprate, actually does a very good single electron transfer reaction and coupling reaction so that you can make a carbon-carbon bond very efficiently. So there are ways to use organolithium couplings, but not with the lithium, but actually adding copper in, and these reactions work surprisingly well for those. And we'll talk about organometallic reagents when we talk about aromatic compounds, because organometallic reagents like this are truly what synthetic chemists use most of the time in the lab. But you have to understand where they're coming from. Okay, so that I just take an aside. We'll talk more about this reagent in the future. Okay, so that is our reactions to form alcohols from Grignards, a little bit about their properties, primary, secondary, tertiary, how to deprotonate alcohols to form alkoxides, and our previous reactions that we learned to make alcohols. What we're going to do next is we're going to talk about the reactions of alcohols and new reactions of alcohols and some old reactions that we've talked about. So that's going to be what we're going to talk about in the next lecture video.